Today in this video I am going to explain Maclaurin's theorem. So according to Maclaurin's theorem, if fx is a function whose nth derivative exists, then it can be expressed as a polynomial function given by fx is equal to f naught plus x f dash naught plus x square upon factorial 2 f double dash naught plus x cube upon factorial 3 f triple dash naught plus so on to x is to the power n upon factorial n f nth derivative naught. Let us prove it now. So first we let that fx can be expressed as a polynomial given by fx is equal to a naught plus a1x plus a2x square plus a3x cube plus so on to an x is to the power n. As by definition, a polynomial is an algebraic expression which can be written in the form of a naught plus a1x plus a2x square plus a3x cube plus so on to an x to the power n. So fx is a polynomial, we have assumed. Now we have to differentiate it with respect to x. So differentiating 1 with respect to x, we get f dash x is equal to a naught is a constant term, so its differential is 0, and a1x, here a1 is the constant coefficient, so we have to differentiate x whose differential is 1, so we get a1 plus a2 is constant coefficient and differential of x square is 2x plus a3 is constant coefficient and differential of x cube is 3x square and plus so on to an as constant coefficient and differential coefficient of x is to the power n is n, x is to the power n minus 1. Let it be equation number 2. Now let us differentiate equation number 2, so we get f double dash x is equal to, now a1 is constant term, its differential is 0, and a2 is constant coefficient and differential of 2x is 2 plus a3 is constant coefficient and differential coefficient of 3x square is 6x plus so on to, and the last term an into n are constant coefficient and differential coefficient of x is to the power n minus 1 is n minus 1, x is to the power n minus 2. Let it be equation number 3. Proceeding in this way, differentiating equation number 3 again, we have f triple dash x. So first term is constant term, so its differential is 0, and the next term differential is 6a3 and plus so on to last term we have n minus 1 an as constant coefficient, and differential coefficient of x to the power n minus 2 is n minus 2 x to the power n minus 3 and so on. Now if we substitute x is equal to 0 in equation number 2, we get f dash naught, and if you observe on the right hand side, each and every term has x except the first term. So if we substitute x is equal to 0 in this, every term becomes 0 except the first term, so f dash naught is equal to a1. Similarly, if we substitute x is equal to 0 in equation number 2, since first term is constant term and the rest of the term of equation number 3 has different powers of x, so substituting x is equal to 0 makes every term 0. So we get f double dash naught is equal to 2a2. It implies that a2 is equal to 1 upon 2 f double dash naught. Putting x is equal to 0 in equation number 4, we have f triple dash naught, and the first term is constant, so we have 6a3, and the rest of the term become 0 because they have different powers of x. So transposing 6 to left hand side, we get a3 is equal to 1 over 6 f triple dash naught. So finally we have f dash naught is equal to a1, or a1 is equal to f dash naught. a1 is equal to f dash naught, a2 as half f double dash naught, half f double dash naught, and a3 as 1 upon 6 f triple dash naught, f triple dash naught, and so on. Further, if we substitute x is equal to 0 in equation number 1, that is in the function, so we get f naught is equal to a naught because rest of the terms have different powers of x, so every term becomes 0 except the first term. So a naught is equal to f naught. A naught is equal to f naught. Now substituting the values of a naught, a1, a2, a3 and so on in equation 1, we get f(x) is equal to a naught, and as we have shown, a naught is equal to f naught, so it is f naught plus second term is a1x, and here we have a1 as f dash naught, so f dash naught x plus third term is a2x square, so a2 is 1 upon 2 f double dash naught, so half f double dash naught x square plus third term is a3x cube, so putting the value of a3 as we have calculated, a3 is equal to 1 upon 6 f triple dash naught, we get 1 over 6 f triple dash naught x cube and so on. Now if we observe f naught as it is and f dash naught x and plus, as we know, factorial 2 is 2, so 1 upon 2 may be written as 1 upon factorial 2 f double dash naught into x square, and factorial 3 is equal to 6, so 6 may be written as factorial 3, so we may write it as 1 upon factorial 3 f triple dash naught x cube plus so on. So finally we may conclude that fx is equal to f naught. If we rearrange the terms, we may write it as x f dash naught, and we may write this term as x square upon factorial 2 f double dash naught plus x cube upon factorial 3 f triple dash naught plus so on. Now, in order to understand the application of Maclaurin's theorem, suppose we have to expand the function e raised to the power x by Maclaurin's theorem. So let fx is equal to e raised to the power x. Now differentiating, we get f dash x is equal to e raised to the power x, because differential of e raised to power x is e raised to power x, second order derivative, again e raised to the power x, third order derivative, e raised to the power x, and so on. So if we replace x by 0 in these functions, we get f naught is equal to e raised to the power 0 is equal to 1, f dash naught is equal to e raised to the power naught is equal to 1, f double dash naught is equal to e raised to the power naught is equal to 1, f triple dash naught is equal to e raised to the power naught is equal to 1, and so on. Now, by Maclaurin's theorem, fx is equal to f naught plus x f dash naught plus x square upon factorial 2 f double dash naught plus x cube upon factorial 3 f triple dash naught, and so on to infinity. We substitute the values of f naught, f dash naught, f double dash naught, f triple dash naught, which are equal to 1 each. So we have 1 plus x into 1 plus x square upon factorial 2 into 1 plus x cube upon factorial 3 into 1 plus so on to infinity. So e raised to the power x is equal to 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus so on to infinity. Let us take another example. Expand sin x plus cos x by Maclaurin's theorem. So let fx is equal to sin x plus cos x, which may also be written as under root 2 sin x into 1 upon under root 2 plus cos x into 1 upon under root 2. So under root 2 sin x, 1 upon under root 2 may be written as cos pi by 4 plus cos x, and here 1 upon root 2 may also be written as sin pi by 4. Here we have written cos pi by 4, which is equal to 1 upon root 2, and here we have written sin pi by 4 in order to make the formula sin a cos b plus cos a sin b format. So in this way we may apply sin A cos B plus cos A sin B, which is equal to sin A plus B. So we have sin x plus pi by 4. Make it 1. Now differentiating with respect to x, we get f dash x is equal to under root 2 cos x plus pi by 4. Again, if we differentiate it, we get f double dash x is equal to under root 2 into minus sine x plus pi by 4, or minus under root 2 sine x plus pi by 4. Differentiating this again, we get f triple dash x as minus under root 2, and differential of sine is cos x plus pi by 4, and so on. Now substituting x is equal to 0 in fx and f dash x and f double dash x and so on, we get, if we substitute x is equal to 0 in equation number 1, we get f naught is equal to under root 2 sine 0 plus pi by 4, that is sine pi by 4, and this is root 2 into 1 upon root 2, which is equal to 1. If we substitute x is equal to 0 in f dash x, so we get f dash naught is equal to under root 2 cos pi by 4, and cos pi by 4 is also equal to 1 upon root 2, so we get root 2 into 1 upon root 2 is equal to 1. If we substitute x is equal to 0 in a next derivative, so we get f double dash naught is equal to minus under root 2 into sine 0 plus pi by 4, that is sine pi by 4, which is equal to 1 upon root 2 again. Root 2 will cancel root 2 and we get minus 1. Putting x is equal to 0 in third derivative, we get f triple dash naught is equal to minus under root 2 and cos 0 plus pi by 4, that is cos pi by 4, which is also equal to 1 upon root 2, and root 2 cancel and we get minus 1, and so on. Now by Maclaurin's theorem, fx is equal to f naught plus x f dash naught plus x square upon factorial 2f double dash naught plus x cube upon factorial 3f triple dash naught plus so on to f naught is equal to 1, so we write 1 plus f dash naught is also equal to 1, so 1 into x, and f double dash naught is equal to minus 1, so if we substitute minus 1 over here, we get minus x square upon factorial 2 f triple dash naught is equal to minus 1, so substituting here minus 1, we get minus x cube upon factorial 3 plus so on to infinity. Now let us take third example, as fx is equal to a raised to the power x. Expand by Maclaurin's theorem. So first we have to differentiate it with respect to x. So we get f dash x is equal to a raised to the power x log a base e. Question number 2, differentiating again, we get f double dash x is equal to a raised to the power x into log a base e whole square, because here log a base e is constant coefficient and differential coefficient of a raised to the power x is again a raised to the power x log a base e, so there will be log a base e whole square. And if we differentiate it again, we get f triple dash x is equal to a raised to the power x log a base e whole cube, and so on. Now if we substitute x is equal to 0 in equation number 1, 2, 3 and 4, we get, in this equation, if we write f is equal x is equal to 0, we get f0 is equal to a raised to the power 0, which is equal to 1. If we substitute x is equal to 0 in equation number 2, we get f dash 0 is equal to a raised to the power 0 log a base e. So we get log a base e. If we substitute x is equal to 0 in this, we get f double dash naught is equal to a naught log a base e whole square, and as a raised to the power 0 is 1, so we get log a base e whole square. Similarly, putting x is equal to 0 in equation number 4, we get f triple dash naught is equal to a raised to the power 0 log a base e whole cube. So we get log a base e whole cube, and so on. Now by Maclaurin's theorem, fx is equal to f naught plus x f dash naught plus x square upon factorial 2 f double dash naught plus x cube upon factorial 3 f triple dash naught, and so on to infinity. Putting the values of f naught, f dash naught, f triple dash naught and f triple dash naught and so on in this expansion, we get f dash naught as we have 1. So 1 plus x f dash naught, we have log a base e, so log a base e plus x square upon factorial 2. F double dash naught is equal to log a base e whole square, so log a base e whole square plus x cube upon factorial 3, and f triple dash naught, we have calculated it as log a base e whole cube. So putting f triple dash naught as log a base e, we get log a base e whole cube plus so on to infinity. Hence we may say that a raised to the power x is equal to 1 plus x log a base e plus x square upon factorial 2 log a base e whole square plus x cube upon factorial 3 log a base e whole cube plus so on.